So it's 43 days if you understand. So perhaps we can start on the YouTube. Good afternoon, everyone. Let us start. So it is my pleasure to welcome Professor Keitaro Takahashi, who is visiting us for some time, mostly for our busy week. And he and his students, as you know, are integral part of Indo-Japanese collaboration, Indian pulsar timing array. So Keitaro is one of the all-rounder in the field of astrophysics and cosmology because he worked on many things, including AGNs, pulsar timing, to cosmology, like you see, epoch of reionization and 20 centimeter cosmology. So it is our pleasure to have you today. So thank you for coming from Japan to here. So today he will tell us about how can I probe the first stars and epoch of reionization using the 21 centimeter line. So please do you.
Thank you very much for introducing me. So I'm Keitaro Takahashi from Kumamoto University, Japan. So this is my first time to visit India, so I'm very excited to be here. And so today we'll be talking about this topic, first stars, so which are stars which were formed for the first time in the history of the universe, and then they emit many photons, like high energy photons like UV or X-rays, and they change the physical state of the universe. So this is called the epoch of Reionization, and they are I think the mystery of the current cosmology. So this can be probed by 21 centimeter line. So this is the outline of my talk. And I assume most of you are not familiar with cosmology. So I'm trying to give a basic review of the cosmology and the epoch of reionization. So let me start with a brief history of the universe. So this figure represents the history of the universe. The leftmost side is the beginning of the universe, which is called Big Bang. And this is the current universe. The history of the universe is about 13 billion years. And the beginning of the universe is called the Big Bang. So this is like a fireball, and the universe was high density, high temperature. And it is a mixed soup of elementary particles. So there's no atoms or nuclei. And after that, the universe expands and it cools. And sometime after the Big Bang, like 0.00001 second after the Big Bang, the temperature gets low, like 10 to the 13 Kelvin. At this epoch, protons and neutrons are formed from 3 quarks. So before this epoch, the temperature was so high that these nuclei cannot be formed, so they are easily destroyed by the photons. And at about 3 minutes after the Big Bang, temperature get like 10 to 9 Kelvin. So and the synthesis of the lighter elements like for helium occurred. So this is called the Big Bang nucleosynthesis. And then about the age of 400,000 years, which is equal to the redshift 1100, the temperature is like 3000 Kelvin. And in this epoch, proton and electron get together to form a hydrogen atom. And so from this epoch, there's less interaction between matter and radiation. So radiation can go freely. And we observe this radiation as a cosmic microwave background. So this is the generation of the cosmic microwave background. And after the recombination of the hydrogen atoms, this period is called dark age. Because the temperature is too low, so below 1000 Kelvin, so there's no optical light. And further, there's no astronomical objects like stars and galaxies. So actually, there's no visible light at this epoch. So this is called dark age. And at a certain epoch, at a certain era, the stars are formed for the first time in the universe. And we don't know much about these first stars, how they formed, what they are like, and when they are formed. We do not know much about this. But sometime after the Big Bang, first stars are formed. And these are called POP3 stars. And it has no heavy elements like heavier than the helium. And this is primordial stars. And then first galaxies are also formed. And it is expected that first stars are much heavier than the current stars like sun. So they can form black holes. And the first black holes must be formed at this epoch also. And approximate age of the universe, of the cosmic dawn, is expected to be like 0.1 giga-year. So this is theoretical expectation. And this corresponds to the redshift 30 or something. But we are not sure about this age. And then the first stars on the first galaxies or first black holes emit a lot of photons like UV or X-rays, high energy photons. And they can ionize the intergalactic hydrogen. So remember, so you remember at the beginning of the universe was very hot and all matter were deformed into elementary particles. And then hydrogen atoms are formed. And again, hydrogen atoms are ionized. So this is called the epoch of reionization. And the corresponding age is like 1 giga-year, and the redshift is like 6 or something. Then 10 giga-year, so redshift 0.5. So dark energy appears at this epoch, and the sun and the earth are formed. And finally, the current universe is like 13.8 giga-year. So today's topic is this epoch, from the dark age, cosmic dawn, and the epoch of reionization. So almost the beginning of the universe. Okay, so me focus on the epoch of reionization. So this is a schematic view of the structure formation of the universe. So in the beginning, so there was a period called inflation. So during the inflation, tiny fluctuation in the energy were generated from the quantum fluctuations. And the density fluctuation then evolved due to the gravity. So in the beginning, the fluctuation was very, very tiny, like 10 to the minus 5 or something. And then due to the gravity, dense region become more dense. So in the end, like this and like this, galaxies or stars are formed in the densest region. So this is the structure formation. So this is the simulation of the first star formation and the epoch of reionization. So this is redshift 24. You can see blue box, and blue color represents the neutral hydrogen and not ionized. And at the redshift 6, this is almost yellow, and the yellow means the ionized hydrogen. So at redshift 24, almost all hydrogens were neutral, not ionized. And then after the formation of first galaxies, they ionize hydrogen around it. And you can see yellow bubble. So this is ionized bubble, so around the galaxy. And in the universe, there are a lot of galaxies were formed, and these ionized bubbles extend and connect to each other, and then the whole universe was ionized. So this is the completion of the reionization. So physical process of the first star generation and epoch of reionization is like this. So at the beginning, there was a tiny density fluctuation, like 10 to the minus 5 or something. And then it is so tiny, and that's evolution is linear. And then at some time, when the density fluctuation becomes large, like 0.1 or something, the evolution becomes non-linear. And finally, the dense region were formed into an object called halo. A halo consists of dark matter and baryons, normal matter. And then baryon gas cooled and formed first stars. And as I said before, we don't know much about the first stars, how they are formed, what they are like. And there are a lot of simulations to study first stars. So, and it is generally expected that first stars are very massive compared to the current stars. So this is the two examples of the initial mass function of first stars. This is the one simulation, and the horizontal axis is the mass, and this is 1 solar mass, 10 solar mass, 100 solar mass. And the mass function is like this. So the peak is like tens of solar masses. So it's much larger, massive than the current stars. And this is another simulation. 10 solar mass, 100 solar mass, 1,000 solar mass. And the peak is like 100 solar mass. So anyway, we can expect first stars are much heavier than the current stars. So this is because there's no metal, heavy elements in the beginning of the universe. So the cooling of the gas is very less effective compared to the current gas. So the star must be much larger than the current universe to cool. And the simulations so predict a much higher, a much heavier stars, first stars. And then, as I said, so these heavy stars will form a black hole. So the first black holes were formed at this epoch too. So as I said, first star produce first black holes. And the first star explodes as a supernova explosion. And then from the feedback of this explosion, the next generation stars called POP2 stars were generated. And this would be much lighter than the first stars because the gas has metal heavy elements. And these objects, first stars, POP2 stars, and first black holes emit a lot of photons, UV or X-rays, and they can all contribute to the epoch of reionization. So they can reionize the intergalactic medium. But we don't know which is the main contributor of the epoch of reionization. This is one of the biggest questions about the epoch of reionization. And there are many probes to study these epochs. So and in this talk, I will focus on 21 centimeter line here. Okay. Let me review briefly the conventional methods to probe epoch of reionization. And there are two conventional ways. One is the CMB, especially the large-scale E-mode polarization of CMB. And this is a map of the cosmic microwave background. The color represents the temperature, and you can kind of see this white line, white curve, which represents the polarization plane of the cosmic microwave background. And from the pattern of the this polarization, we can get the optical depth of the cosmic microwave background photons. So CMB photons can be scattered by the free electrons. So from the optical depth of the cosmic microwave background photons, so we can know the amount of free electrons from the CMB production to the observer. So from the observation, the optical depth is like 0.1, so which means that about 10% of the CMB photons were scattered during their way from the production to the Earth. And from this, we can evaluate the electron density in the intergalactic medium. And if we assume the instantaneous reionization, the reionization occurred at about 10 or something. So this is a very rough estimation of the epoch of reionization. And Gunn-Peterson test is another probe of the epoch of reionization. So this can probe the intergalactic matter ionization rate from H1 absorption. So this is the spectrum of a quasar at a high redshift, like redshift 6 or 7 or something. And from this spectrum, we can know the density of the neutral hydrogen. And from this, we know that reionization was completed at redshift 6 or something. So these numbers are representative number of epoch reionization. So these are what we know and what we don't know about the epoch reionization. And what we know is the reionization proceeded around redshift 10, and it was completed at the redshift 6. And the residual neutral fraction is about 10 to the minus 4. Not all the neutral hydrogen were ionized. And this is, there was a tiny residual neutral fraction. And this is all what we know currently. And these are what we don't know. So what kind of objects contributed to the reionization? So as I said, so POP3, POP2, or AGN, or black holes can all contribute to the epoch of reionization, but we don't know the main contributor. So black hole may be the main contributor, or POP3 or POP2. And we know the completion, the epoch of completion of ionization, redshift 6, but we don't know the time evolution of the ionization fraction. And we want to know when first stars formed and how they were massive. And we also want to know first black holes and how heavy they are and when they are formed. So these are what we want to know, we don't know. And to study these things, one of the very powerful tools is the 21 centimeter line. So what is 21 centimeter line? So this is physically the hyperfine structure of the hydrogen atom. So this is the hydrogen atom, which consists of a proton and an electron. And so they have both spin 1/2. And if the spin is parallel, this state has a slightly larger energy than the anti-parallel state. The energy difference between these corresponds to the 21 centimeter line. The frequency is like 1.4 gigahertz. So with this 21 centimeter line, we can probe a neutral hydrogen. So the neutral hydrogen can emit or absorb 21 centimeter line, but ionized hydrogen cannot. So from this 21 centimeter line, we can probe the neutral hydrogen. Okay, and actually, we don't observe 21 centimeter line as they were. So due to the cosmological expansion, so for example, 21 centimeter line emitted at redshift 6, redshifted to about 200 megahertz. And redshift 20 corresponds to 70 megahertz. So these are the target frequency of the epoch of reionization 21 centimeter line. So with this very low frequency radio waves, like 100 megahertz, we can observe cosmic dawn and the epoch of reionization tomographically. So because this is a line, so we can know tomographically. So here, let me introduce a very important quantity, which is related to the 21 centimeter radiation. So it's called spin temperature. And the spin temperature is defined like this. This is spin temperature. And this is the number density of the anti-parallel state, ground state. And this is the, do you have another one? A stick. So this is the number density of the parallel, so excited state, and this is the ground state. So the ratio can be expressed as a Boltzmann distribution, and this is the spin temperature. So essentially, the spin temperature represents the ratio, abundance ratio between ground and the excited states. And you must remember that in the universe, there were always cosmic wave CMB photons. So we have always a radio wave in the universe. So what we observe is the absorption of the CMB or emission of the 21 centimeter beside the CMB photons. So they offset from the CMB, okay? So this is the CMB, and we observe this CMB radiation. But in between, there must be some H1 clouds. And if this cloud has a lower temperature than the CMB temperature, CMB photons were absorbed into this cloud. So we observe less photons expected from the CMB radiation. On the other hand, if the cloud has a higher temperature, higher spin temperature than the CMB temperature, we observe more photons than expected from the CMB radiation. So So we observe the difference between the spin temperature and the CMB temperature. So how the spin temperature is determined? So there are three processes which affect the spin temperature. And one is the interaction between the CMB photons and the neutral hydrogen atoms. And with this interaction, the spin temperature is approaches to the CMB temperature, TCMB. The second process is the atomic collision. So this couples the kinetic temperature of the gas with the spin temperature. So the gas kinetic temperature and the spin temperature is a different temperature, okay? And the efficiency is represented like XC. And the final process is the interaction with ambient Lyman alpha photons. The interaction between the hydrogen atoms and the Lyman alpha photons. And this couples the color temperature, which is defined by the spectrum of the ambient Lyman alpha spectrum. So the spin temperature is affected by these three temperatures: CMB temperature, kinetic gas temperature, and the color temperature. And physically, these two temperatures are almost in equilibrium. So they can be assumed to be the same. So spin temperature is affected by these two temperatures. And this figure represents the expected evolution of the spin temperature. So, but before that, let me explain the CMB temperature, the behavior of CMB temperature, and the gas kinetic temperature. So this is the redshift. This is a higher redshift and a lower redshift, and this is temperature. And this blue line represents the CMB temperature. And the CMB temperature behavior is very simple. It just cools down with expansion as inverse A scale factor. So just like this. And then gas kinetic temperature. So it also cools with expansion, cosmological expansion. But because this is a non-relativistic fluid, this cools down like A minus 2 inverse A squared. So this cools much faster than the radiation. But at some time, the gas can be heated by the formation of galaxies or stars. So they emit high energy radiation, and the intergalactic gas can be heated. So it rises like this when the stars and galaxies are formed. So this green line. So first they cool down, and at some time at the formation of the galaxies, they are heated like this. Okay. So these are CMB temperature and gas temperature. So let me go back to the spin temperature. The spin temperature, the evolution of the spin temperature is represented as this red complicated line. So actually this behaves very complicated. So as I said, the spin temperature is affected by both CMB temperature and gas kinetic temperature. And sometimes the spin temperature approaches to the gas temperature, and sometimes it approaches to the CMB temperature. So it is determined by the efficiency of the interaction between hydrogen atoms and CMB or other thing. And in typical model of the cosmology, the evolution of spin temperature will be like this. So first, they approach it to the gas temperature, and then after some expansion of the universe, the atomic collision becomes less frequent due to the dilution of the hydrogen atoms. So the spin temperature approaches to the CMB temperature. And at some time after this, so like redshift 30 or something, the And the Lyman alpha photons were emitted by first stars or first galaxies or first black holes. And at this epoch, they again approach to the gas temperature. And then the spin temperature rises with the gas temperature. So in a typical model, the spin temperature behaves like this. It is very complicated. And the former half of this evolution is we are confident about the evolution of this epoch, because this is determined almost all by the cosmology, which we know very much. But at this epoch, this involves the big uncertainty involved with the astrophysical process, like star formation or galaxy formation. So we are not so confident about this epoch. So we can probe this epoch by measuring the spin temperature. So as I said, the observational quantity is the difference between the spin temperature and the CMB temperature. So this is the CMB temperature, and this is the spin temperature, and the observable quantity, the difference between these two temperatures. And that is called the brightness temperature. And this is the expected spectrum of the 21 centimeter signal. And this is frequency, and the low frequency, which corresponds to higher redshift. So for example, frequency 50 corresponds to redshift 30 or something. And this is a higher frequency, which corresponds to lower redshift. And this is the brightness temperature, and this is 0. So if the spin temperature is exactly the same as the CMB temperature, the brightness temperature is 0. But there must be some difference between the spin temperature and the CMB temperature. So this is the difference. So this is the observable quantity. So as we saw, in the first half of this evolution, the spin temperature is lower than the CMB temperature. So in this epoch, the signal is absorption. So that corresponds to this epoch, so below 0, so which means the absorption. And after that, the signal becomes emission like this. So this is because the spin temperature goes up like this. So this is emission compared to the CMB. Okay, so this is the expected signal. And from this spectrum, we can probe the epoch of reionization, which is low redshift in this figure, and cosmic dawn and dark ages. But unfortunately, so look at the frequency here. So from the surface of the Earth, there is a lower bound which we can observe, the lower bounds on the frequency, which we can observe. So below 50 megahertz or 30 megahertz, the ionosphere can reflect the cosmic radio wave. So we cannot observe these low frequency range. So we cannot observe or probe dark ages from the Earth. So we must wait for something like a lunar telescope or like that. So from the Earth, we can observe these epochs, cosmic dawn and epoch of reionization. So I don't explain so much about specific models of the epoch of reionization, but I just want to show the variation of the models and corresponding signals. So for example, one of the parameters of the model, epoch of reionization model, is the X-ray intensity of the galaxies or black holes. So X-rays can hit the IgM gas, and the source could be a quasars or X-ray binary or supernova or something. And the emissivity of the X-ray depends on the initial mass function, a binary fraction, or something like that. And if we vary the X-ray intensity of the object, the signal changes like this. This black line is the fiducial model, but if we increase the X-ray intensity like 100 times, it becomes like this blue one. So because X-ray can hit the IgM, so there's no absorption. So they hit the IgM very quickly. So the similar example is this. So if we vary the intensity of Lyman alpha, the signal changes accordingly like this. So from the observation of this spectrum, we can know the intensity of X-rays or Lyman alpha of the galaxies at this epoch.
Just one question.
Mm-hmm.
So is it by changing the neutral hydrogen fraction that these things are modified? But how this goes on?
So they change the spin temperature. Okay. So because so for example, X-ray can hit the intergalactic medium.
But the neutral hydrogen fraction remains the same.
Yeah, so it depends on the epoch. So actually, so at this epoch, the neutral hydrogen gets more ionized. So the signal can be reduced. But at this epoch, the hydrogens are almost neutral. So before the redshift 20 or something. So X-ray can affect the signal through the spin temperature. Okay, so now we want to think about the fluctuation of the 21 centimeter line. So actually what we considered so far is the average spin temperature of the universe. But there must be some fluctuation, spatial fluctuation of the spin temperature and the brightness temperature. So the brightness temperature fluctuation is expressed like this. So it depends on the ionization fraction at a position and baryon density, baryon over density, so baryon density fluctuation, and the spin temperature, which also depends on the spatial position, and the peculiar velocity. So these four quantities affect the observable brightness temperature. So if we perform a very idealized observation, we will get images like this. So you remember that we can observe the neutral hydrogen. So the epoch before the reionization can emit a lot of 21 centimeter line. So the image is like this. So after the reionization, there's no neutral hydrogen. So there's no signal like this. So when the reionization begins, there must be ionized bubbles like this. So these are the fluctuation of the 21 centimeter line. So and if we can get the images like this, so and we can find the ionizing bubble like this, so there must be a source of the ionizing photons here. So 21 centimeter line cannot observe the source itself. So we need the multi-wavelength observation, like optical or sub-millimeter. So if we observe here with the JWST or ALMA or something, so we can observe the source of this ionized bubbles. So there are two ways to observe the epoch of reionization with 21 centimeter lines. So one is the average temperature, which is called the global signal. So this is the average temperature of the universe. So what we obtain is like this. And from this, we can know the evolution of spin temperature. And more interesting is the fluctuation of the 21 centimeter line. So from the fluctuation, we can get the images like this. Or if the signal to noise is not so good, we can measure the statistics of the fluctuation, like power spectrum or something. So, so first, we will be able to measure the statistics of the signal. And then if we have enough sensitivity, like SKA, so we will be able to do imaging of this epoch. So this is the theoretical expected evolution of power spectrum, so which quantifies the fluctuation of the 21 centimeter signal. And this is the redshift, so higher redshift and lower redshift. And there are a lot of models. These are the evolution of the power spectrum. And so the evolution of the signal reflects the physical processes which affect the H1. And they are dependent on the model parameters. And in this figure, several models are shown. So for example, so look at this blue line. So the rise is here. And there are some peaks. So 1, 2, 3 peaks. And these peaks reflect the physical processes, like the interaction between the Lyman alpha and hydrogens or something. And so the signal, the evolution of the signal, highly dependent on the parameters of the models, like this and like this. And on the other hand, the sensitivity of the telescopes like MWA, HERA, and the next generation SKA are also shown here. So this is the sensitivity of the MWA located in the Australia. So this telescope can measure the 21 centimeter signal of low redshift, like redshift 10 or something. And one of the next generation is the HERA, located at South Africa. So this is now being constructed and beginning to do the observation. So this has a much higher sensitivity like this. So the observation will extend to the redshift like 20 or something. And this is the sensitivity of the SKA. So this has a much higher sensitivity than HERA and MWA. So this will extend to redshift like 25 or something. So this is exactly the redshift of the cosmic dawn. So with the current telescopes like MWA, we can probe the epoch of reionization, relatively low redshift like 10 or something. And with the SKA, we can study much higher redshift, like 20 or 25, which corresponds to the cosmic dawn, first star formation. And let me show you some of the studies of our groups. And actually, so this is the power spectrum of the fluctuation. So in cosmology, we measure fluctuations with the power spectrum. And this is enough. Power spectrum is enough if the fluctuation is Gaussian statistically. But actually, in fact, the signal of 21 centimeter line is highly non-Gaussian, not Gaussian at all. So power spectrum is not enough. So we can get more information with the higher order statistics like bispectrum or Minkowski functional. So we calculated these higher statistics to extract more information from the observation. This is an example of the calculation of the bispectrum. So this is the expected constraint on the model parameters. So this is one model parameter, which represents the emission efficiency of the UV photon. And this is a parameter which represents the mean free path of the radiation. And this green circle represents the constraint, expected constraint from the measurement of power spectrum. And on the other hand, from the bispectrum, the constraint will become much tighter than the power spectrum, like this. So we can add information from the measurement of a bispectrum. And this is an example of the Minkowski functional. So Minkowski functional is a bit a difficult quantity, and which measures the shape of the map. So this is the 21 centimeter signal map, and we can quantify the shape of these bubbles or fluctuations somehow, and we can show this shape like this as a function and a function. So from these quantities like bispectrum or Minkowski functional, we can get more information which cannot be obtained by the conventional power spectrum. So this is our approach.
Sorry, what is the source of this non-Gaussianity? I mean, what is
source of the non-Gaussianity?
Is that due to some interaction, or what is that?
Yeah, the one simple reason is that. So if there is a source here, so it can make a bubble. So this is very non-Gaussian object. So in this region, the fluctuation is similar to Gaussian fluctuation. But if there are some bubbles, that makes a very large non-Gaussianity.
So the reionization is the reason for the non-Gaussianity.
Yeah.
If there is no reionization, then it would be Gaussian. Is that
not exactly? But reionization is the big source of the non-Gaussianity. Okay, so 21 centimeter line for the study of dark age, cosmic dawn, and the epoch of reionization. And this is the new probe of these epochs. This is the 21 centimeter line comes from the hyperfine structure of the hydrogen and can directly probe the intergalactic medium. And this is actually the measurement of spin temperature compared to the CMB temperature. And the observation can be done with the global signal, which is the average temperature of the universe, and the fluctuations. And as you saw, the cosmic dawn and the epoch of reionization are very complicated mixture of cosmology and astrophysics. So cosmologists and astrophysicists must work together to study this epoch. So finally, I will explain about the current status of the observation of 21 centimeter line. First of all, so one group has claimed the detection of the global signal, so which is the average temperature of the universe. So the group has performed the experiment called EDGES. It's about 5 years ago. And they claimed that the detection of absorption of the global signal at 70 to 80 megahertz, which corresponds to redshift 15 and 20. So this corresponds to the epoch of cosmic dawn. So that was very exciting, if that is true. So this is one experiment. So this must be confirmed by other experiments. So now many experiments are doing the similar analysis and observation. So this must be confirmed. This is the global signal. And on the other hand, the fluctuation of the 21 centimeter line has never been detected yet. But several experiments, several telescopes are now trying to detect the fluctuation of the 21 centimeter line. So these are the telescopes now ongoing. The MWA in Australia, and the LOFA in Europe, and HERA in South Africa. But they are doing very hard analysis and observation, but the signal has never been detected yet. And the largest obstacle to detect the 21 centimeter line is the huge foreground. So the foreground is the radiation between the signal and the observer. So the signal comes from the redshift 6 or 10 or 20. It's very far from the observer. And in front of that, there are many galaxies and Milky Way radiation objects. So these are foregrounds. And typically, the signal of the EOR 21 centimeter line is 5 millikelvin. And on the other hand, the foregrounds. So for example, galactic foregrounds, which consists of synchrotron and free radiation, is typically 5 Kelvin. So this is much higher than the what we want. So like 1,000 times the expected signal. So this is a huge foreground. And also there must be some extragalactic foregrounds, typically like 1 Kelvin or something. So this is the biggest obstacle to detect the signal.
So the signal would be redshift.
Yeah.
No, it is not. So then how is the foreground a background for this thing?
Sorry?
How is this a background? I mean, couldn't it be separated by just redshift?
So these emissions are continuum. So
And so it falls in that window.
Yeah.
It's not a line feature, is it?
They are not line, but hydrogen signal is a line. The red shifted to 100 megahertz or something. And these are continuum, which extend from low frequency to high frequency. So this is a very famous map, Hasselblad map at 400 megahertz. And this is the galactic plane. And this is very bright. So as I said, so this is typically 1 Kelvin or 10 Kelvin or something. So the foregrounds are much larger than the signal by 3 orders. And if we count it in the power spectrum, it's 6 orders larger than the expected signal. So we must mitigate the foreground somehow. And one good point is the spectral feature is very different from the signal, 21 centimeter signal and foregrounds. And in general, foregrounds are has small, smooth spectra, like power law, so like this, while EOR signal has non-smooth spectrum. So this reflects the distribution of the H1 cloud. So it's not smooth, but rather so like this. So this is the cartoon of the detected signal. So this is the combination of EOR signal and the foreground. So foreground is like this, and the signal is like this. So if we can remove the smooth component of the observed spectrum, so we can extract this EOR signal. But it's not easy because the smooth foreground is 1,000 times higher than the expected signal. So so far there are 3 strategies to mitigate the foreground. And I don't explain much about that. But so there are three major strategies. The one is subtract the foreground. The second is to avoid by going to the Fourier domain. And finally, cross-correlate with other probe like galaxies or something. Sorry?
When you say it is smooth,
yeah,
how smooth is it?
How smooth? That's a very good question. Typically, it has a power law spectrum, but because the expected signal is 1,000 times smaller than the foreground, so the foreground must be smooth by that level. And we are not sure how smooth they are actually, but we hope they are very smooth at that level. And this is the current status of the observation of the signal fluctuation. So this is the redshift and the lower redshift, like 6, and higher redshift, 20. And these are expected signal, theoretical power spectrum. It's typically like 10 millikelvin or something, below 10 millikelvin. And these are the current upper bounds on the power spectrum at each redshift. And so currently, the upper bounds are much larger than the expected signal, the typical signal. So like 2 orders in power spectrum. But actually, it's getting better and better because originally the foreground is larger than the signal by 6 orders in power spectrum. So originally the foreground is like this, and now we subtract the foreground to this level, and another 2 orders. Okay, and this is the prediction of one extreme model. So we are now beginning to constrain some extreme models, but not the typical models, not yet. So this is the current situation.
It's just that you showed that it's not in the plot.
So it is the global signal, so it cannot be put here.
Yes. Sorry. These arrows are, is it telling they were done this experiment in all the frequency because the redshift is span is, that redshift span is telling the different frequencies, right? Whatever.
Yeah, different.
Are they done in the different frequencies in the?
So lower frequency here. And higher
frequency
here. Yeah.
So that observation done in all the frequencies you are telling, because you are mentioning all the papers there, is it?
Sorry?
Yes. Arrows, are they mentioning observation in all the frequencies, like different frequencies?
Different groups. So
Different groups.
different groups are shown with different colors.
Power in that redshift, which means are they done the observation that frequencies?
Yeah.
So it's okay. It's a span of multiple.
So this is like 100 megahertz.
Yeah, correct.
This is like 80
80, 10,
yeah.
100 megahertz. Yeah.
So this is the future prospect.
Just one more.
Okay.
Sorry.
So sorry, the edges experiment, those arrows on the top, they are dating back previous to their experimental results, or those numbers come post? So in timeline, the edges experiment of 2018, I think, right? The arrows above the same redshift range, 15 to 20. 15 to 20, yeah. Redshift number 15 to 20, yeah. Yeah, those upper limits have been have come out before the experiment or after the experiment, I think.
Experimental edges, you mean?
Before the edges results.
I think after the edges experiment. So generally, lower frequency observation is much tougher, so difficult to analyze. So there was no motivation before this experiment. But after this experiment, I guess there's much motivation they have, and they obtained these upper bounds, I guess. Okay. Okay, so this is the future prospects of this field. And now, some of the experiments like MWA or HERA or LOFA are now ongoing, and they can be called the escape zero. Actually, they are pathfinders or precursors of the SKA. And I guess within several years, they may detect the signal, the first detection. So the first detection will occur within a few years, I expect. After that, SKA1 will appear, and it will do the precise measurement of the power spectrum. And in the era of SK2, it has enough sensitivity to do the imaging of the signal. And to probe the dark age, so below the 30 megahertz or something, so we need a lunar telescope or something. So this is the future prospect. Okay, so let me summarize. So I talked about the frontier in the cosmology. So dark age, cosmic dawn, and epoch reionization. So we want to know about the first stars, first galaxy, and the first black holes. But so far, these epochs are probed by CMB mode or Lyman alpha forest. And we will soon have a new probe of 21 centimeter line. And the observation is very difficult. And the analysis is also difficult because the signal is very tiny and we have a huge foreground. And now ongoing telescope will do the first detection within a few years, I guess. And in the latter half of the 2020s, we will have the SKA, and which will open a new era of the study of the cosmic dawn and the epoch reionization. So thank you very much for your attention.
Thanks, Keitaru, for such an interesting talk. So questions? Yeah.
So how the cross correlation techniques with the other probe is helping you to reduce the foreground?
So it's one way of the foreground mitigation. So for example, so if we subtract the very smooth component of this foreground and we get this, so if we get this, we are not sure if we subtracted the foreground completely, but there must be some residual in here. So to be confident we have the right subtraction or right signal, we can cross-correlate the signal with the other probes like galaxies. So as we saw, okay, this image. So this is the ionized bubble. So there must be some sources here, here, here. So if this is the correct signal, and when we cross-correlate with the distribution of galaxies with the 21 centimeter signal map, there must be a negative correlation. So, in this way, we can be confident in the subtraction of the foreground.
Distribution of the galaxy, cross-correlating distribution of the galaxy with the foreground subtracted signal.
Yeah, foreground subtracted map with the galaxy map.
But that's not the galaxy map is not the continuous thing, right? Then how?
So like so we must know the redshift of the galaxies. So higher redshift galaxies like redshift 6 or something, and we can correlate with the